Okay, thank you. So this is a subduction zone. It is where one tectonic plate moves underneath another tectonic plate. Earth's surface is made up of a collection of tectonic plates that are basically discrete pieces of the surface that are free to move. Most people in the United States are standing on the North American plate. We're standing on the North American plate. A few people in California are standing on the Pacific plate. And in Hawaii, they're standing on the Pacific plate. These subduction zones are host to some of the largest and most destructive natural disasters that can happen on Earth. We get arc volcanism, megathrust earthquakes, and earthquake-related tsunamis that can be highly destructive. Despite how destructive they are, we don't really know why they happen in certain places more often than others. For example, Seattle, for some reason, has almost no earthquakes, while northern Japan has a ton of them. They're both on top of subduction zones. We don't know why that is. A lot of modern research points to the role of water in the subduction zone as sort of regulating these processes. So the subducting plate brings water down, and when the subducting plate warms up, it releases water, and that water can move up into the overriding plate, or it can be trapped on the interface between the two plates. And my research focuses on trying to understand what controls where the water goes, what the water does, how much water is down there. These are all open questions. One possibility is that the water interacts with the rocks in the upper plate and it hydrates them. So that hydration induces a volume expansion, and that volume expansion cracks the rock, much like a bottle of wine left in the freezer expands and shatters, or the frost cycles here in Minnesota destroy our roads. So that volume increase induces cracks, and that crack allows more water to flow into the rock, and that allows the reaction to proceed more volume increase, more cracks, et cetera, et cetera. So we ran numerical simulations on the supercomputer to understand how this process controls fluid migration in subduction zones, and we identified two sort of key crack patterns that depend on some local parameters. In places like Seattle and Osaka, we expect water to migrate into the overriding plate. We don't know what it does when it gets there. In places like Sendai and Santiago, we expect a crack pattern that deflects fluids along dip. They may migrate up dip, where they lubricate the interface and cause earthquakes, or they may be dragged down, where they feed arc volcanism. It's not really clear which one. It's an open question. Thank you.